First, a correction from what's in the schedule. The exam schedule has this at 3:30, and I accidentally have it at 1 on the class schedule. And, of course, I am required to go by the exam schedule. So the exam is at 3:30 on Monday, not at 1 on Monday like it says in the schedule. I apologize. I didn't realize that mistake until I was preparing this lecture. Yeah. It's at 3:30 on Monday. And Tioni, you weren't here when I was talking to Connor and Daniel. You were the only three that still have to do the STAR final thing. And I am hoping, against hope, that either Saturday night or Sunday night, it'll be clear and you guys can do it then because it's so much better. And so I'm not going to give you the paper one today. It's just going to do the review for everybody because otherwise I have to split you guys off. You go do that and skip the review. And after the exam, if you haven't had a chance to do it, then I'll give you the provisional on paper.
Okay. So you said Saturday night is okay?
Saturday night's okay, yeah. Yeah.
Is this Friday night or not?
That is correct. Okay, so the exam is cumulative. So it's going to cover units 1 through 74, I believe it is. I didn't look very carefully to make sure 74 is where we ended, but it was somewhere in that vicinity going through the galaxies, the beginning of galaxies. So the question that's going to be the biggest single question for the exam is going to be, once again, the scientific method question. Going back to the first day of class, I emphasized one of the real goals I want students to get out of this class is to understand the scientific method, because the scientific method is the philosophical framework, really, of how we identify what we believe to be truth scientifically. And so you need to be able to write down exactly what is on that sheet, just like on exam 1. The question will look just like on exam 1, except for it to be a different observation. So you'll need to reproduce that, and then after reproducing it, I will say, you observe blah, and I will give you a statement, and then you will have to apply the scientific method to that specific statement. So if I say, hey, Russell, if I say you observe that, and I gave you the example before, pies taste better when you eat them or not pies, ice cream tastes better when you eat them at Cold Stone Creamery than if you eat them at the actual dairy. Then for step 1, you would restate the observation. So you would write down, I find the pies taste better at Cold Stone Creamery than at the dairy. And then for step 2, you need to have a hypothesis that's based on scientific ideas to explain why that occurs. So you need to say something that's going to, in layman's words, say, I think that they taste better at Cold Stone Creamery because of this that's based on a scientific reason. So when I gave you that example, I talked about we know scientifically that our sense of taste is related to our smell. And so it could be that it smells like cow manure at the dairy, and that's why they don't taste as good there. Right, but it needs to be based on a scientific idea. It needs to explain why the observation occurred. Then for step 3, you need to devise a test that would test a prediction. So the prediction is that, or the hypothesis is that smell affects taste. So then an actual test would be to, let's just isolate, let's remove everything else and just see if the smell changes the way it tastes. So you come up with an experiment that, changes the smell and have people rate the taste. And then the final step, you do have to have the final step, and the final step would be if this outcome occurs. So in my example, if when people have a foul smell and they eat the ice cream, they rate the ice cream as not tasting as good, then my hypothesis is confirmed. It's not proven, right? Never proven. But it's confirmed, and I would go back and test another way to see if it is disproven in different testing. If, on the other hand, people who are eating the ice cream with the putrid sewer smell say, wow, that's the best ice cream I've tasted. It's much better than the other stuff. well, then I disproved my hypothesis and I have to go and make a new hypothesis. So you have to actually state those things. Don't just say if passes and if fails, but say what the pass state is and what the fail state is. So does everybody understand that part of the test? Because that's the biggest chunk of points. If there's confusion, then you don't get the points and then I'm not happy. Not to mention you. Okay, so we've got the scientific method. You should know that. It's how we get information. So now other things we have from part 1. Remember, exam 1 was over both parts 1 and parts 2. So the other things from part 1 were knowing what types of things we find in the sky. Now, at this point, we've studied a lot of things we find in the sky. We've studied galaxies just a little bit. We've studied the clusters. We've studied stars, the different types of stars. We've studied our planetary system, the planets and the moon. And so at this point, it's a lot easier to say, yeah, those are the things we find in the sky. We also want to understand things like how astronomy relates to our definitions of a day, of a month, of a year, how calendars relate to astronomy. So make sure you have just understanding of how we use astrological measurements. Astronomical? to define things in our lives. Yeah, the words are different. Make sure you know the difference in a lunar eclipse and a solar eclipse and what causes them, why we don't have a lunar eclipse every time we have a full moon, why we don't have a solar eclipse every time we have a new moon. The way we identify things in the sky, make sure you're clear on what right ascension is, what the declination is, what direction the Earth rotates. Now, we're going to go into the history here, and we also need to know about the history, when they thought that everything went around the sun, the Ptolemaic model, the Aristotelian first, then the Ptolemaic, and then moving to the Copernican model, and finally going to the way we believe things are. Well, I say finally, Galileo, the sun is the center, going to where we are now that says there is no center, but we orbit around the sun orbits around the center of the Milky Way galaxy, and the Milky Way galaxy is moving through space in what we didn't get to this, but we believe to be a universe of infinite size. How many constellations are there?
There's a lot.
How many keys are there in a piano?
32.
Depends on the piano.
Piano. On the standard piano.
I believe it's 88 on the piano. I know it's 88 constellations.
It's 88 on the grand piano.
On a grand?
No.
What's called uprights and grands.
Okay. So we have 88 officially recognized constellations. Ken was giving me grief saying, the real challenge should be for a student to find 15 different cultures that use the same set of stars for a different asterism, so that they could point to the same thing and go 15 times on the same one for the lab final. He thought that was funny. I thought, oh boy, that'd be a problem. You can only use an asterism once. You can't give it a different name and use it again. Okay, new rule. Asterisms are less formally defined star pictures, whereas constellations are areas in the sky. So within those 88 constellations, you cover the entire sky exactly once. No star can be in more than one constellation, so that's why Alpheratz is now only part of Andromeda and no longer part of Pegasus. It's still part of your connect the dot picture for Pegasus, but it's not part of Pegasus because it can't be part of two constellations. Okay, going to some history things. In order to understand, and actually, I guess history was on that one. In order to understand astronomy, you have to understand some physics. And this, I know, was probably the least enjoyable to my students because it really gets bogged down in a lot of math and whatnot. But some important ideas there. Inertia. What does inertia mean? I'm pretty sure that you both said the right thing. I could be wrong in both counts because I was splitting my attention. But inertia is the propensity of an object to stay in constant motion. So if something's moving, it just keeps moving the same direction, the same velocity, same speed. That's what inertia is. That wasn't understood back in the time of Aristotle. He thought that you had the natural positions, things naturally want to be on the ground type of thing. And you had natural motion. The natural motion was get to that natural position and stay there. And it's Galileo that really gave us our clear understanding of things in motion want to stay in motion. And then Newton, who gave us the law, Newton's first law, that says things will stay in constant motion unless something acts on them. Why is that important to astronomy? Because we have things like the moon out there. The moon, if nothing was acting on it, would just keep going in a straight line. And so we would say bye-bye, right? But it doesn't go away. It stays there, which means that there must be something acting on it, something pushing on it to make it stay with the Earth. And what's the force? The force is anything that pushes or pulls that's keeping the moon with the Earth. Gravity. So we have to have some gravity understanding to understand how we can have orbits. And that force of gravity, always attractive. And that attractive force is always proportional to the product of the two masses. That's proportional to mass 1 multiplied by mass 2. So you are really far away from the center of the Earth, but you have a really strong force pulling to the center of the Earth because it's such a massive, massive Earth. You have a force attracting to everybody in this classroom, but that's really small, even though you're close, because their mass is small. So that force of gravity, it came into play later when we talked about stars, because that force of gravity is what pulls the star together to begin with. It's what creates the temperatures and pressures in the core so fusion can occur. It's what's going to continue to crush it as it dies. So gravity is, in my opinion, the most important of all of the forces in astronomy. There are only 4: strong nuclear, weak nuclear, and electromagnetic and gravitational. But I consider it the most important because it's the one that always wins in the end. So in the sun, it's not winning right now. We're in equilibrium, but eventually it's going to win. So we have to have these ideas of physics. Kepler's laws, remember Kepler had 3 laws. What did those laws relate?
Sorry, I just saw my grade for the last time.
Oh, was it good?
Yeah.
I told you not to worry.
That's what I was dancing.
What do Kepler's laws have to do with?
Orbits.
They have to do with the orbits, specifically Kepler's laws are the orbits of planets around the sun. And so Kepler had 3 laws. The first one, all of the planets are doing elliptical orbits around the sun. How is that different from Copernicus?
Yeah, exactly.
Copernicus had circular laws, or circular orbits. And the circular orbits didn't match reality. The observation of the position of the planets with time didn't quite match up. There were little variations. Well, with the elliptical orbits, it was spot on. And Kepler recognized that by just looking at the data and saying, well, does it fit with the circle? What would it fit with? Maybe we stretch it. So that's his first law. The sun is at one of the focal points. So we come closer to the sun, we go farther away, closer, farther away. The second law then says that the area swept out by a line going from the sun to the planet is constant in time. Which, to you and me, what was our take-home message from that?
The farther away it is, the slower it moves.
The farther away in its orbit from the sun, the slower a planet moves. So you have something like Mercury, which has a reasonably eccentric orbit. It moves much quicker when it's close to the sun than it does when it's far from the sun. It's because of that that the moon, which is tidally locked, the same side of the moon always faces us, it's not perfectly always facing us. It has the little, what was the word for it? I don't remember it.
Was it wobble?
No, it was some kind of Asian. I don't remember what it was. But it has a little bit of back and forth motion as you look at it from Earth. it's not really going back and forth. It's rotating at a constant rate because it has constant angular momentum. But when it gets closer to the Earth, it's going faster. And so its rate of rotation appears to change from us. It appears to change angle. Okay, so then this third law. The third law is the one that we do use an equation for. That's the one that says that the period squared in units of years is equal to the semi-major axis in astronomical units cubed. So we learned later using Newton's laws, when Kepler came out with these laws, they were just laws that he came up with no physics reason for them, just they seemed to be correct. And then Newton, with his laws of physics, was able to explain why these were correct. Well, if there's laws of physics, then with his calculus. And with Newton's explanation, we found that it actually depends on the mass, not of the planet, but of the star that it's orbiting. Or if we talk about the moon, it would not depend on the mass of the moon, but the mass of the Earth that the moon is orbiting. And so we can relate the period squared, the semi-major axis cubed, and the mass of things that are orbiting each other. And so Kepler's third law becomes really important. Kepler's laws are all important, but the third one is the one we do a lot of math with. Now let's go back to the second law, comets, right? Because comets is one of the things we're covering. What is a comet?
What do you ask? What is a comet?
Halley's Comet is a comet.
Halley's Comet is a comet. That's a true statement. But what is it?
Ball of ice and rock.
It's a ball of ice and rock. It's a ball of ice and rock that comes from either the Kuiper Belt or the Oort cloud, far distances from the Earth. And these objects normally do pretty circular orbits because during the flattening of our solar system, you might recognize the flattening process of the formation of our Milky Way galaxy and the flattening process of our solar system were exactly the same description. In fact, the entire process of forming our solar system, the process of forming the galaxy were the same process, just for a different size. So all of those objects in the Kuiper Belt are all going in the same direction in circles, but every now and then things come too close, gravity takes over and throws something in toward the sun. And when it throws it in toward the sun, as it gets close to the sun, the solar wind and the radiation from the sun causes it to have material that is vaporized, melted, goes into a gas phase, and then gets blown off. And so the comets are just ice balls getting close to the sun and being, melted by the sun. And that melted material is blown away from the sun. The ion tail is directly away from the sun. The dust tail will be mostly away from the sun because of solar pressure, but also will trail behind it a little bit. So with the comet now, where's it going to spend most of its lifetime? Close to the sun or far away from the sun?
Away from the sun.
Why?
Because it only comes around the sun for a slow time. So, because it's slowly traveling away.
Okay. The key here is the second law, Kepler's second law. It goes really slow when it's far away from the sun, really fast when it's close.
Yeah, I didn't say it like that.
Yeah, but you were in that ballpark, yes. So Kepler's laws are important for us to understand the motion of stars, the motion of moons, the motion of comets. It's an important law for us. Angular momentum is the idea that if you don't have something to provide a torque, rotation rate will stay the same. And so for something like Aldwin sitting in a chair, if he has mass as close to his body, his moment of inertia is small, and he'll spin faster. If he brings them farther away, mass is farther from his body, and he'll spin slower for the same angular momentum. Why is this important to astronomy? Because let's take something like a pulsar. Pulsars rotate at as much as 1,000 times a second. What would happen if a star rotated 1,000 times a second? What do you think would happen? It would just be shredded because everything would have so much momentum, its inertia would just take it away. So the star couldn't possibly have been spinning that fast. So how do you go from a massive star that's spinning maybe once every 20 days to this tiny neutron star or pulsar that's spinning 1,000 times a second.
Do we know how fast the rest of us? How fast the rest of us?
Roughly 22 days. It depends on if you're at the pole or the equator. That's where I got the number from.
You dead no matter what. It's still,
Huh?
you dead no matter what. If you're at the pole of the equator.
Oh,
Yeah.
the sun has a longer period at the pole and a shorter period, so it goes faster.
I'm just saying, if you're standing at the pole or at the, you're dead no matter what.
Oh, you're dead no matter what. Yes, okay. That's the word I missed. Okay, so how is it possible for this relatively slow rotating star to become a very fast rotating pulsar? Radius shrinks and the conservation of angular momentum may spin up. That was also the reason we have those glitches that are observed in pulsars, that they're slowing down over time and all of a sudden they'll jump up in speed. I believe they must be compressing when they jump up in speed. What units do we use for temperature in astronomy class? Kelvins.
It's the same thing.
They're not the same thing.
I mean,
They're
it's
offset by
all-
273.15.
But at that temperature, does that really matter?
He has a good point. At that temperature, at the temperature in the core of the sun, what's the temperature in the core of the sun?
Like 15 million Kelvin.
Like 15 million kelvins. How much is that in Celsius?
Like 15 million Celsius.
15 million plus 273. Well, that plus 273 is meaningless. So the temperature in the core of our sun, yeah, it doesn't matter which one you use. But if you're talking about the temperature on the surface of, let's say, the surface of the Earth, the temperature on the surface of the Earth is somewhere around, let's say, 20 degrees Celsius, or somewhere around, 300-ish, 293 kelvins. Well, then it makes a huge difference. And kelvins are the standard unit we use in science. How is it possible for an atom to absorb light? Light comes in, it hits an atom. What has to happen in the atom for it to absorb light?
The electron has to jump up.
You have the electron jumps up to a higher energy level, so this might be minus 13.6 electron volts, and this would be, what's 13.6 divided by 4?
Why would you divide it?
Did I say, I meant to say divided by 4, did I not?
But why would you divide it?
Just to be correct. Because that's what the energy levels are for the bottom and the next energy state for a hydrogen atom. So if I have a photon that comes in and the energy of that photon, remember the energy of the photon depends on the frequency. So we have energy equals h times frequency, where h is a constant. If this energy is exactly equal to the difference between those two, so if that's equal to 10.2 electron volts, then the electron can absorb the energy. The electron goes to a higher energy state and the light disappears. If the energy of that photon was 10.1 electron volts instead of 10.2, no dice, it just goes through. So it's because of the distinct, unique energy levels of the electrons that we have absorption of light. Now that electron goes to the higher energy state, what's it naturally going to do once it gets to the higher energy state? It's going to come back down all on its own and make a photon come out that has that same energy. So understanding this is important, once again, to interpreting what's going on in stars. We can measure this on Earth. We've got all kinds of experiments we can do on Earth to show that this is what goes on with atoms. And then we look at the sun, or we look at a distant star, and we say, ooh, I see absorption at this frequency, which means I have an energy gap between electron states of this amount. If I were on Earth, what atom would have energy differences of this amount? And we can start identifying the atoms out there based on our physics here at home.
Or physics is different there, though. Is it just that we're assuming that it's the same?
Yes, and if we'd gone to the cosmology chapter, that's one of the, you have your cosmological principle, which includes universality, which says the laws of physics are the same at all places in the universe at all times. It's an assumption. No, the laws of physics are the same everywhere at all times. That's what universality is, including black holes. And that's a fundamental assumption. And if it's wrong, then a lot of our understanding of the universe is going to be wrong.
Right.
So you need to be convinced that that's a reasonable assumption. And certainly there are people who are not convinced it's a reasonable assumption. You can go and you can find lots of people who argue that the speed of light, which depends on the electromagnetic force, they suggest that that changes with time. And if the speed of light changes with time, then that means that the electromagnetic force strength changes with time. And if the electromagnetic force changes with time, then that throws into question pretty much all of our understanding about how we determine what atoms are present, the measurements of Doppler shifts, all of these things get confused then. So it's kind of important to understand what the assumptions are so you can determine, do I have confidence in, do I have faith? You know, I have faith in a lot of these things in science, but I tell you what, when it comes down to it, I have more faith in God. And so if I have a situation where my science really appears to say A, and my interpretation, my best interpretation of the Bible says B, I'm going to go with the Bible because that's where I have the most faith. Because you got to have faith. Much like...
You got that? Faith.
I kept myself from singing it though. George Michael would say, got to have faith. Baby. Okay. You're not asking me to stay. Anyway. What's the difference in brightness and luminosity? We just had this on the most recent homework.
Brightness is what it appears like.
Yes.
Luminosity is what
Okay. It's hard to define brightness without using the word brightness, isn't it?
Yes.
You were going just like me. Brightness is how bright it appears. But I just said the same word twice and you can't define it by itself.
It's like trying to define what it looks like.
What?
It's like trying to find what a color looks like.
Yes. Actually, no, because for all we know, colors could look different to different people.
Yeah, that's why it's like.
Then we're getting into philosophy.
Yes. So that's brightness and luminosity. If we know the brightness and luminosity, what other thing do we automatically know? With a little math.
Let's go with that location.
Yeah, the distance. Because the brightness decreases as the light spreads out over a spherical shell, so it decreases with the area of a sphere, which is 4 pi r squared. So if you...
What's the three things you need to figure out? It's brightness, luminosity, and...
Well, if you know it's brightness and luminosity, you can get the distance. Or any two of those, you can get the third. Now, we also had another homework question with the Stefan-Boltzmann law. If you know the luminosity and the temperature, what do you know? That was one of the homework questions, exactly. Well, no, it said, how does the Stefan-Boltzmann law allow us to help us define the radius? Because if you know the luminosity and you know the temperature, you can calculate the radius from, so there's a lot of these mathematical things you can determine. If you make these measurements that are easy, then you can determine this one that's not so easy.
I feel like the scientific method is all just the definition of insanity, doing something over and over again, expecting a different outcome.
No. You don't expect a different outcome.
You just hope it.
You hope it has the same outcome. And you don't actually do the same thing over and over again because you test it different ways. So you're not doing the same test.
Still feel like it's insanity.
Now, science lab, yes. In science lab, we do the same test over and over and over. And hopefully it never turns out differently. Okay. So we talked about the Stefan-Boltzmann law here. What about Wien's law?
We just talked about that.
Yeah. So what about Wien's law? Wien's law relates the peak wavelength to the temperature. And so one way we can determine the temperature of an object is by looking at what wavelength is its peak. But that's not how we actually determine the temperatures of stars. How do we actually determine the temperature of stars?
Computer modeling.
We determine the temperatures of stars by looking at the relative strengths of different absorption lines. Because as we did in that lab, we saw that the population of n equals 1, well, n equals 2 is what we did in lab. The population of n equals 2 for hydrogen atoms is the greatest at around 10,000 kelvins. If the temperature is lower, there's not as many in n equals 2. If the temperature is higher, there's not as many as n equals 2 in n equals 2. But n equals 2 is where the electron has to be if you're going to have a Balmer absorption. So Balmer absorption will be strongest if it's around 10,000 kelvins, and it'll drop off on either side. So one thing you do is you measure how strong is the Balmer absorption. And then you measure now, how strong is the Paschen absorption? How strong is the Lyman absorption? If it's hotter, it's going to have more Paschen absorption. If it's colder, it's going to have more Lyman absorption. And so by looking at the relative strengths of the absorption, you can then determine the temperature. And that's actually the method that's used because it's more accurate. You don't have to worry as much about the atmospheric absorption than using the Wien's law. But Wien's law is useful. We can use that to calculate the temperature of the sun based on the peak radiation of the sun. So you should be able to do that. Stefan Boltzmann law, since I put Wien's law, the Stefan Boltzmann law was luminosity is equal to, which for a star can just be written as that. Oh, then we have telescopes. All the excitement. What do you need to make a telescope?
Lenses.
Lenses or mirrors.
Preferably both.
Yes, preferably both. Usually if its primary optical device is a mirror, we call it a reflector. If the primary is a lens, we call it a refractor, because refraction is the bending of light when it goes from one material to another. Refraction not only is the reason lenses work, it also explains things as simple as why stars twinkle. Stars twinkle because you have air currents with different temperatures, and as the light from the star goes through the different temperature air currents, it bends, it refracts. How does a telescope take that into account?
It's like the mirror.
Not that one, what did you say?
Doesn't it like star and
Yeah, what we can do is we can actually make a deformable mirror. And you have to have a bright star that you use as a guide star. And you look at how that motion of the star from the bright star is moving. And then you deform your mirror in a way that would have kept that stationary, stabilized it. And then you can look at some star nearby and you'll see a stabilized picture that takes out the twinkling, which is pretty miraculous. You can only do that, though, with a reflector, one that has a mirror. Reflectors are better for so many reasons for astronomy. Number one, no chromatic aberration. Doesn't matter what the color is, it's going to come to the focus the same place. With a lens, different colors focus different places. So you actually have an error in your image based on color. With a lens, the light has to go through the lens and you have absorption through the glass. With a mirror, it just reflects off the front surface, and so you have no absorption of anything by the optic. You only have to grind one surface for a mirror. You have to grind two for a lens.
It's cheaper.
It's cheaper, much cheaper. You don't have to have as much material. It can be much lighter. You can easily support the entire thing. With a mirror, you can't support the entire thing. Your light's not going through it.
You can make it bigger.
Yes, they can make them bigger because it's easier to hold them and it's easier to make them. Mirrors are used for all of your recent astronomical telescopes, including the Webb Space Telescope I will add.
What is your telescope?
The Webb Space Telescope, yes. Or if you want to be all kinds of specific, it's the James Webb Space Telescope, but who knows James Webb, right? He was, I think, the first head of NASA. And as far as I know, no relation to him. Okay, so make sure you understand telescope.
You said no one listened to him?
What was that?
No relation.
No relation, yeah. He did not have, well, I do not have his blood flowing through my veins. Okay, other things with telescopes. What's the importance of a telescope to astronomy? That's a very simple question, but just to make sure you recognize what's the point or why are telescopes important? Yeah. They're the only way we know anything about astronomy, pretty much. Now, we do have spacecraft that have traveled through our solar system, but as we've seen, our solar system is just a little minute portion of the universe. Anything else in the universe, all we know about is what we get from telescopes. So we have telescopes that are pretty sophisticated, and they don't just look at what our eyes can see. They don't just look at the visible light. We also have telescopes that look at infrared light. Infrared light can kind of get through the atmosphere. We have telescopes that look at radio light. Radio light can readily get through the atmosphere. We have telescopes that look at ultraviolet light. Well, that can't get through the atmosphere at all. And so you have to have it orbiting the Earth, or at least high in the atmosphere so there's not much atmosphere, to use one of those telescopes. We have these different telescopes because we can learn about different things. If you have a microwave telescope, that's going to tell you about things that are relatively cold. If you have an ultraviolet telescope or an X-ray telescope, it's going to tell you about things that are hot. And so you can determine more about specific temperature ranges using these different telescopes. Okay, then our solar system. You should know our solar system pretty well. You should know the planets in the solar system. You should know about their moons and about their own unique properties, like which ones have atmosphere and which ones have moons. And don't ever make the mistake that Titan and Triton. I swear when I was doing that, I was thinking, well, Neptune's the one that has the, in my head, it was Titan. But no, he doesn't have a Titan. He doesn't have a god. He has a Triton, a little three-sided or three-point sphere.
Titan was in Titan.
Hmm?
Titan. Is it Titan?
Yeah, Titan goes with Saturn.
No, he's a Titan. Not a god.
Oh, well, to me, Titans are gods.
There's a difference.
There probably is.
There is much difference. So gods are the children of Titans.
The mythology is weak in this one, okay? Okay, radiometric dating, good physics. Basic things you need to know about radiometric dating. Let's say how do I determine the age of the Earth? One way is by radiometric dating, looking at rocks and determining how old they are by the dating method. Another one is looking at the sun, looking at where it is in the main sequence, right? Because it's going across that main sequence. And by looking at where it is, we determine it's about halfway through its lifetime. Based on its mass, we determine its lifetime is about 10 billion years. So we say, it's about 5 billion years old. Look at the oldest rocks. The oldest rocks that are found in the solar system so far are about 4.6 billion years according to radiometric dating. Well, how do you get them? You guys just had a homework question where you went over how you get the age of a star, how long it can live, right? The luminosity and the mass relationship. Well, radiometric dating, the key fact is that radioactive decay is just the nucleus falling to a more stable state, and it's just statistical. So given a certain amount of time, there's a certain percentage likelihood that it will decay. And so based on that statistic, we define a time as the half-life when there's a 50% chance of decay. And so if I have a sample that contains let's go with a magical number, contains 100 radioactive nuclei. Let's say it's 100 carbon-14 nuclei. The half-life for carbon-14 is 5,730 years, plus or minus about 20 years. So how long do I have to wait until I have only 50 radioactive carbon-14s?
15 or 50?
50.
How much did you say?
I started with 100. Or to put it another way, I started with 100%. How long do I have to wait till I have 50%?
One half-life.
One half-life, because that's the definition of the half-life. The time when half of them will decay, because it was the time when there's a 50% probability of decay.
That's what I thought you were talking about, so I just went.
Good call. Okay, so what about, how long would I have to wait to have 1/8 remaining?
The number of half-lives.
3 half-lives, because 1 half-life I'd have 50% remaining. 2 half-lives I'd have half of 50%, so 1/4. 3 half-lives I'd have half of a half of a half, 1/8. And so that's the method that's used for radiometric dating. Now, there were some idiosyncrasies, things like you have to know how much there started to know, how much is gone. And how do we know how much is started? Because no one was here, right? No one was here on Earth 4.6 billion years ago measuring, saying, oh, this rock has this much. You wouldn't use carbon-14 for 4.6 billion years ago. You might use uranium, or you might use potassium. It had this much potassium-39. Nobody was here to do that. So we have to have some calibration methods. So with something like carbon-14 dating, which is only useful to add about 50 to 100,000 years at the most, we find things that we can date either by archaeological methods or by growth patterns, and then measure how much they have of the radioactive element now compared to the non-radioactive, and calculate, well, it has this half-life, it has this percentage now, how much did it have when it started? And that's how they actually do the calibration for carbon-14 dating. So they do not assume a constant amount of carbon-14 in the atmosphere. Everybody knows that would be wrong. A lot of creationists try to accuse scientists of doing that, and that's one of those straw man arguments. You set up a premise that's untrue, and then you say, and that makes no sense, and cut it down. But they actually, the scientists know this, and they calibrate it. For something like potassium argon, it's a much more complicated system they use to be able to calculate how much there was initially. So scientists aren't going off and being stupid. They're being smart about these things, which makes it so I have a hard time disbelieving radiometric dating. At the same time, recent, like last decade evidence suggests that things like proteins are still around from dinosaurs. And according to everything we know about biology, that's impossible. It's impossible for that protein to be viable after 100,000 years. You've got a T-Rex that's 65 million years old, they believe, with protein. And so that means that maybe we're wrong. We're either wrong about our biology or we're wrong about our physics in that. Okay.
They're arguing with each other about who's wrong.
Yes, it's a touchy subject. Like initially, people refused to do testing because they didn't want to come up with results that would be hard to explain.
Isn't that the entire point of science?
Excuse me?
Isn't that the entire point?
Yes, it is. But scientists are still humans with frailties. Like, I don't want to be the one that tells everybody, pulls the rug out from under.
That's like the best. That's like being the best job.
It kind of is. Okay, sticking with the topic because we only have 7 minutes left. Geology on Earth. Why did we want to understand geology on Earth for astronomy?
Learn about geology.
Yeah, Earth happens to be a planet, just like Mars.
But we can study lots of geology now.
We can now. And we can study Venus somewhat, for an hour at a time at best. A few $1 billion for an hour's worth of study time probably isn't the best laboratory. But we can study the Earth and then use that to try to figure out what happened on other planets. So we look at Earth with its plate tectonics and motion, and then we look at something like Mars. We say, does Mars have plate tectonics? Right now, no. But maybe in the past, we have the deepest canyon in the universe is
solar system?
I will just say Mariner Trench to put it in English.
You mean the solar system?
Solar system, I said Earth.
You said universe.
Universe, yeah. Solar system, definitely solar system, is that Mariner Valley in English. It's deeper than Earth and is believed to have been the result of plate tectonics in the past on Mars. But it doesn't have the evidence of plate tectonics now. In fact, we have the tallest mountain in the solar system, Olympus Mons, that exists on Mars, and it doesn't even make the crust sink in. The Earth, the crust sinks quite a bit under the tallest mountain on Earth, which is Mauna Kea in Hawaii. Mauna Kea is not the highest elevation because it starts underwater in the ocean. We have the lowlands on Earth, which are underwater in the ocean, basaltic. We have rifting. We have the highlands, the continents. We have those same types of things on other planets. So understanding it on Earth helps us to apply to other planets to understand them. So that's why you need to have these basic things about geology and the Earth's magnetic field. It protects us. It's created, we believe, because of the swirling molten material in our Earth. If we look at stars, stars have magnetic fields. We believe that's from swirling, conducting material with convection in the stars. In the stars, that's going to be the ionized hydrogen. In something like Jupiter, it's going to be liquid metallic hydrogen. In something like like Neptune and Uranus, it's going to be a briny salt water. Different materials, giving you different behaviors. So you have those very weird magnetic fields of Uranus and Neptune. Right? They're really tilted. They don't go through the centers. You have the reversal of the Earth's magnetic field, every couple 100,000 years on average. You have the reversal of the sun's magnetic fields every 13-ish years, 11 to 13 years. All of these things are, if we can understand them on Earth and study them on Earth, we'll understand them better when we look and see them out there elsewhere.
Is the sun's reversal of its magnetic field why it goes to those phases?
Is what?
Is the sun's reversal of its magnetic field why it goes to the sunspot phase?
It's actually more the other way around, but the two are combined, right? That when the magnetic field lines get so tangled up, you have just sunspots all over the place close to the equator. That provides a force that causes the sun to go through its reversal. So the two are definitely tied together. Okay. I've talked about this enough here. Except for dwarf planets. Dwarf planets. Pluto, Ceres, Eris, et al. How many did I skip?
Like the 10 billion behind Pluto.
Well, dwarf planets, there are only 5 recognized. So I skipped Makemake and Haumea. Mostly because I have a hard time remembering those two. Notice it says know all about comets, asteroids, and meteors. It doesn't say know all comets, asteroids, and meteors. So we've talked about comets already. Asteroids, where do we find most of the asteroids? In the asteroid belt, which is where?
Between Mars and Jupiter.
Between Mars and Jupiter. How did that asteroid belt form?
Goes to Jupiter.
Is what?
Goes to Jupiter.
Okay. It's not a 100% certain answer. But one of the theories is maybe you had a forming planetesimal between Mars and Jupiter, and the strong gravitational force of Jupiter tore it apart. We have, of all of those asteroids, the vast majority of the mass of all the asteroids is in one asteroid series, the dwarf planet. Most of them are really tiny. Really tiny meaning like, a kilometer or less. And if you were to fly through the asteroid belt, what would it be like?
Nothing.
Like nothing. If you were to watch Star Wars, it'd be this crazy dodging game, right?
Wait, you said like
There's
asteroids
very,
like
it's very,
But-
very few and far.
They're few and far between. So you'd basically just be, set your course.
So
It's like missing islands in the ocean.
And like,
You really don't worry about
actually, you'd be surprised how many times people get islands in the
it. I probably would. But
you will be surprised.
okay, meteors, generally it's just debris left behind by a comet. The Earth is flying around the sun. When it hits that debris, it burns up in our atmosphere and we see meteors.
For example, have you ever heard the story of that tree that was in the middle of the Sahara Desert? The only tree in the Sahara Desert when someone hits it.
Yes, I actually know that story. Meteors, if it hits the ground, what do we call it? A meteorite. So if it hits the ground, it's a meteorite. The light we see is a meteor. The object out there is a meteoroid. Almost all meteoroids are cometary debris.
Isn't it,
All meteorites are asteroids.
Unless it was a fairy tale.
wasn't it if you clump all the asteroids in the asteroid belt together, it wouldn't even be enough to make a planet the size of that Earth?
No, it's like 1/80th or something like that. It's a small fraction.
Would it still be bigger than Pluto?
I don't know.
Dr. Flynn?
We'll finish right here. Make sure you know about the sun, its atmosphere, what's going on from the core out. So you have the the radiation zone, where heat takes a long time to get out because it's doing the random walk, the convection zone, where it only takes like a month to get out through that part. You have then the photosphere, which is what we think we see a surface of. Above that, you have the chromosphere, then you have the corona. Make sure you understand about sunspots and all those things. And you can do the Obi-Find-Gal-Kiss-Me for the spectral types. You know your luminosity types for the stars.